Hello everyone, my name is Aarohi and welcome back to my channel. So guys, so far we have understood the complete working of encoder in transformers, and today we will understand how decoder work. But before we begin guys, a small request: if you find these videos helpful, then please like and share them, and also feel free to comment if you have any questions or suggestions. Now let's begin with today's topic, and guys, we will work with the same input sentence. So this was our input sentence. My name is Aarohi and I love coding. This input sentence we gave to the encoder, and then encoder gave us this output. The output of the encoder is a matrix of shape 8 into 512. What is this 8? 8 means the number of tokens in our input sentence. So we have 8 tokens over here. And what is this 512? This 512 is a D model. So guys, if you don't know what D model is and what these things are, because inside encoder we have performed all these steps. First we performed tokenization, then embedding, then positional encoding, after that self attention, multi-head attention, and feed forward neural network, then residual and layer normalization, and then we stacked all the encoders. So all this part we have already covered, and if you don't know what these things are and how to use them, then please check this playlist. So first 8 lectures are on encoder only, and today we'll start with the decoder, and the encoder output is this. And guys, always remember that encoder will finish its task first, and after that decoder will start the work. Means the decoder starts only after encoder is done. And why it is so? Because decoder needs information about the input sentence, and that information is provided by the encoder. So in our case, encoder has completed its task already, and it produced a output matrix of shape 8 into 5 and 2. That means we can work with decoder now. So suppose the task we want to perform is to generate the next 5 lines after our input sentence. So our input sentence is my name is Aarohi and I love coding. Now decoder will generate the output, which is the next 5 lines. And we know that transformers generate one word at a time, and all the previously generated tokens become its input, and this is called auto regressive generation. And in attention is all you need paper, there are 6 decoders stacked one after the other, and each decoder layer has 3 sublayers. First one is this masked multi-head attention, and the second one is this multi-head attention layer, which is basically a encoder decoder attention, and it is also known as cross attention layer. And the third one is this feed forward network. So these are the 3 sublayers inside decoder. Every decoder will have these 3 sublayers, and we are also using add and normalization after all these sublayers. Same like in encoder also we use add and normalization after these layers. In the same way, in decoder also we are using add and normalization after every sublayer of the decoder, and these are the 3 sublayers of decoder. So this masked multi-head attention layer, what it does? So this layer will only look at the tokens which decoder generated. Guys, it has nothing to do with encoder output. This layer over here will only see which token, the tokens which decoder generated. We will understand this in detail. Right now, I'm just giving you an overview what each layer does. From here, you will give the input to the decoder, and here you will get the output of the decoder. Suppose decoder generated this token, my token. Now, this is the token which decoder predicted. Now, this token it will become the input. Now, on this input, we will perform the embedding. We will add positional encoding. So, my token will be converted into a embedding. So, D model is 512. So D model is 512. That means this my token will be converted into a vector of size 512, 1D vector. So you will have 1D vector like this, and in this 1D vector you are going to have 512 numbers. Then this positional encoding vector will also have 512 numbers in it. Then you will perform element wise addition on it and you will get a final vector of size. What will be the size, guys? How many tokens right now we have over here? We have only one token. So that means you will have a matrix 1 into 512, because here right now we only have one token. So that one token is going here. And then the masked multi-head attention will work on it. So what we are learning over here, that masked multi-head attention is working on the tokens which are generated by the decoder. It has nothing to do with the encoder output. And then it will go to the add and normalization layer. Then we have this multi-head attention layer. This layer, guys, this layer is this one, encoder decoder attention, which is also known as cross attention. Over here, we are using the encoder output. So encoder output, the output which we got after the sixth encoder, that output which is of shape 8 into 512, that output we are using over here. And guys, only at this step we use the encoder output. So we will discuss this also in detail. Right now I'm just giving you an overview, and after that we have feed forward network. And guys, this feed forward network is exactly the same which we studied in encoder. After that we have this linear layer, and finally we have softmax layer. This softmax layer will provide the probability values for the vocabulary. Guys, what is vocabulary? If you remember from our first or second class on LLMs, this class, there I have explained you the concept of vocabulary. I have told you vocabulary simply means how many unique tokens your model know. And over here at this step, what will happen? This softmax activation function will provide the probability values to the vocabulary. Suppose if you have 50,000 unique tokens, that means for these 50,000 tokens, softmax will provide the probability value, and the token which will have the highest probability will become the next token, predicted token. So you can see here, okay, so like this, probability of my is, let's say, this, probability of name is this, probability of coding is this, and probability of AI is this. Like this, for all the 50,000 unique tokens which we have, we will get the probability values. And this token has the highest probability value. That means this token will become the next predicted token. Means over here, you will get the name token then. Now let me explain you all these layers in detail. So initially, when the decoder starts, the first step it takes is to prepare the input. So the decoder's input is the tokens it has generated so far. Means the decoder's input is only the tokens which it has generated previously. And when decoders start working for the first time, there are no tokens as input. So at the very beginning, decoders start with the start of sequence token. This start of sequence token. Okay. Initially, here which token we will have? SOS means start of sequence token. So first we will have a embedding vector of this token. Okay. You will get a embedding vector. And what will be the size of that embedding vector? That embedding vector size will be 512. Means you're going to have 512 numbers in that vector. You will have a one vector, and how many values you are going to have in that one vector? You are going to have 512 values in it, numbers in it. And after that, we will use this positional encoding. Why? Because we also want to send the position of each token. Right now we have only one token, but in some time you're going to have multiple tokens, then you need to send the position of each token. So that's why we are using positional encoding. And for positional encoding also, you're going to have a vector, and you're going to have how many numbers in that vector? 512. Guys, embedding vector and this positional encoding vector, the numbers which you're going to have in 1D vector depends upon the D model, and in our case, let's say the D model is 512. Now you will perform element wise addition on it, and after element wise addition, you're going to have a 1D vector of size 512, because we have performed element wise addition. After positional encoding, this is what you'll get. Okay, what is it? We will have 1D vector, and that 1D vector have 5 and 2 numbers in it. This will become the input to the decoder. This XDEC means decoder, and this 0 means we are working on a first decoder right now, and we have 6 decoders. So right now we are working with the first decoder, and then the second, then third. Okay, so right now this is the input to the masked multi-head attention. Now let me explain you in detail what is happening inside this layer. So I've told you this is the initial token. Okay, when your decoder will start the work for the very first time, this will be the input token. That means over here we have only this token. Now, after embedding and positional encoding, I've told you we got this input. Now, inside this masked multi-head attention, we are going to calculate query, key, and value. Guys, remember we have calculated the query, key, and value in encoder also. So I'm not going to discuss this in very detail. If you don't know what query, key, and value is, then check this video over there. I have explained in detail. Today we are not going to cover this in detail. Okay, so to get the query, the input, this input will be multiplied with the weight matrix of query, and to calculate the key we will multiply this same input with the weight matrix of key, and to get the values we will multiply the same input with the weight matrix of values. And these weight metrics are initially randomly initialized, and then these matrices learn with time. Right now we have only one token because initially work has started, and this is the only token which we have. So we will get a query, key, and value for one token. That means the matrix which we are going to have is one by one attention matrix. Guys, remember what attention matrix means? In attention matrix, you have the number of rows and columns as per the tokens. So let's suppose if you have 8 tokens in your sentence, then you will have 8 rows and 8 columns. If you have 256 tokens, you will have 256 rows and 256 columns. Row simply means queries and column means keys. So the very first time when you're using the decoder, at that time you will have a matrix of 1 by 1. So mask is allowed. Now what this mask is, guys, over here, first we will calculate the query, key, and value. After calculating the query, key, and value, masking is applied so that future tokens are hidden. This simply means that each token can attend to itself, and to its previous tokens, future tokens are not visible to it. Mask allowed over here simply means that this token can attend to itself. There is no need to hide any token over here because we have only one token over here. Now let's take one more example. Now suppose when we gave this token as input, this token over here, and then the decoder worked on it. First decoder will work, then second decoder, and like this all the 6 decoders will work on it, and then the output of the final decoder will go to the linear layer, and then it will go to the softmax layer, and softmax layer gave the highest probability to I token. Okay, so I token. So that means this I will become the token over here. And second time, while predicting this third token, these two tokens will be the input to the decoder. So the masked multi-head attention layer will take these two tokens which are generated by decoder as input. So this time, see, the input matrix will be of shape 2 into 5 and 2. Why? Because this time it has two tokens over here. So this input keeps on changing after every next word generation, and you will calculate the query, key, and value every time like this. Every time when one word is generated and decoder is going to generate a next word, at that time query, key, and value will be calculated using this updated input. Right now, which token is at position 1? This token is at position 1, right? And which token is at second position? I token, right? So these are the two tokens we have right now, and we will get a attention matrix of size 2 into 2. Why? Because I've told you that you will have the number of rows and number of columns as per the number of tokens which you have. So we have two queries, that's why we have two rows, and we have two columns because we are calculating the keys also. And rows are queries. What are rows? Rows are basically queries, queue, and columns are keys. Okay. So, how do we calculate attention metrics, guys? We are talking about that we are getting 2 by 2 metrics or we are getting 1 by 1 metrics, but that attention metrics, how do we calculate it? So, we will use the same formula which we used in the encoder. Remember, we use this formula, and in the paper, this is the formula. So, the first part of that formula is multiply query with the key transpose, means multiply all the queries with all the key transpose and then scale those values. And what is this decay? How you will get the decay? Decay simply means d model, which is 512 in our case, divided by number of heads, which are 8, and you will get a 64. So this is the decay, and in every query and key vector you're going to have number of values which are equivalent to 64. Means in every query and key vector you're going to have 64 numbers in it. And in the same way, in dv you are also going to have 64 values. That means each value vector will have 64 values in it. So this kind of attention matrix you get. So right now our attention matrix is small because we only have two tokens. First token is this and second token is this, and rows are queries and columns are keys, and we have some values over here. Why these values are looking like this? Because right now we haven't used softmax on it, so these are the raw scores. Next thing is to apply mask on it. Remember, I've told you just a few minutes back that masking will hide the future tokens from the decoder. Okay, so that part we want to do now. So see here, this token can attend to this token, but this token cannot attend to I token. So that's why we have this negative infinity over here. Negative infinity is basically a mask. This negative infinity is basically a very large negative number, and I will show you in some time how we are handling it. So right now just think that this is a mask. That means this token can see to this token, but this token cannot see the future token, which is this. Okay, and I token can see this token also, and I token can see this token also, right? So this is what we are doing. And after that, once you get the attention scores, remember guys, in encoder also I have told you that once you get the attention scores, then we use softmax on it. So in the same way we are applying the softmax on it. So this is the formula of softmax, and first row is this 3 and negative infinity. First, I'm showing you how to solve it. Then we will see the second row. E raised to the power 3, this 3, which is the first number in the matrix. So e raised to the power 3 is this, and e raised to the power minus this infinity is 0, because it's very close to 0. So that's why we wrote 0 over here. Now you sum these, you get this, and you will solve it using this formula, and you get these two values 1 and 0. Now guys, this 0 simply means this position is masked. This means that the token which is over here, that token contributes nothing. Its value vector is ignored completely. And masking simply means blocking the future tokens. And this is what we are doing over here. Now, over here, what we got? 1 and 0. And 0 simply means this position is masked. Now, let's see the second row, which is 2 and 5. See, second row have these two values. Again, exponential of 2 is this, e raised to the power 5 is this, and when you sum, you'll get this, and then you'll get these probabilities, and this will be your final attention probability matrix. And in this matrix, only this position is masked, because this token cannot see I token, because I token is the future token, but I token can see this token and this token. And from this attention matrix, we understood that this I token is attending a little to this token, and I token is mostly attending to I token. Like this, for every next token generation, this process will be followed. And this is not the final output yet. Right now, we only used query and key vectors. So if you remember from the encoder class, there also we, after calculating the attention matrix, we multiplied it with the value vector, remember? So that part we are going to do over here also. So this is the final formula. We know what we performed, this also we performed scaling, also we performed softmax also. Now we will multiply the value vectors with the output which we got from previous step over here, query and key attention matrix. So that's what we are doing. So this value vector we have already calculated above. So our value vector is this. Right now we have only two tokens, so we will work with those two tokens. So the value vector of this token will be a 512 dimensional vector, and value vector of I token will also be a 5. No guys, not 512. This is a mistake. We will have a 64 dimensional vector. Why 64 dimensional? Remember, dv dv is 64. How we got 64? Because d model divided by number of heads is equal to 64. So dk and dv both are 64. So over here, value vector of this SOS token will be a 64 dimensional vector, and value vector of I token will also be a 64 dimensional vector. So this is the first row of the attention matrix, and this is the second row of the attention matrix. And see, we are performing multiplication over here, and we got the values now. So the shape after this step will be T into 64. T into 64. T means number of tokens, okay? And 64, you know why we got this 64 over here, why we are using this 64, because dv is 64. So the output matrix which we get after the single head will be t into 64. And guys, if you remember, in encoder we used 8 heads, and I've told you what head means. Head means separate self attention task which are getting computed parallelly. So in the same way, in decoder also, in decoders, this layer also, which layer we are studying? We are studying, let me go to the top and show you. So right now we are studying about masked multi-head attention layer. This layer we are studying about. So inside this layer, when we are calculating this query key and value, so this is the task of one head. Over here, in this masked multi-head attention, we have 8 heads. That means 8 such tasks are getting performed parallelly. So we have 8 heads. All the 8 heads are working parallelly, calculating attention parallelly. And that means we are going to have 8 such matrices. You will have 8 output matrices of shape T into 64. Next step is to perform concatenation. Guys, again, this part is already explained in the encoder, this video. You can check this video. This concept we studied in encoder also, the same concept we are using over here. So these are the 8 heads we have. Then we performed concatenation on it. Concatenation simply means putting all the heads output side by side. And after that, we are using this WO. This WO matrix we are using for linear projection. What this linear projection means, you can see in the previous video only. I am just giving you a overall idea that the purpose of this WO matrix is to combine the features, to combine all the attention matrices together, so that we can have one 1D vector for one token, and all the information which is there in the all 8 heads, we can get that information in a combined manner. And after this step, you will have a matrix of shape T into 5 and 2. So this is the output of masked attention layer. After that, we have add and normalization layer. Okay, let me show you the architecture once. Here, see, we performed task over here, and the output of this masked multi-head attention is T into 512. And if you remember, the input which we gave to it was also of shape T into 512. And guys, these shapes should be same, means output of each sublayer of decoder should be T into 512. Why? Because the input to the decoder is T into 512. And if these shapes are different, then you cannot perform element wise addition on it. So over here, see, this input we are adding with the output which we get from masked multi-head attention. And if the output of masked multi-head attention is something different, let's say you have output T into 786, but the input to this multi-head masked multi-head attention is T into 512, then you cannot perform uh, addition on it. So that's why the shape should be same, and all the layers in the decoder will have same shape, which is T into 512. And now the shape is same, we can perform element wise addition on it, and we can perform normalization. So you can see here, this is the formula we will use. See, this is the formula. Input to the decoder is T into 512, and T is number of token. And the output of the masked multi-head attention means this is T into 512. So you can perform element wise addition on it, and then you can perform normalization on it. So this is the next step. After that, now we will use the next sublayer, which is cross attention sublayer. And guys, this is the part where the output of encoder will be used. Remember, the output of the encoder is 8 into 512. Over here, we will use that. So guys, this cross attention sublayer will have two inputs. First input will be the encoder's output, and encoder's output is 8 into 512. And the second input it will get from the previous layer of decoder. Okay, so previous layer of decoder. And guys, see here, queries are coming from decoder, keys and values are coming from encoder. See, XDEC, this means decoder. And for query and key, we have mentioned XENC. ENC means encoder. That means queries are coming from decoder, from here, the step which we have performed from here, and keys and values are coming from encoder. So this XDEC is basically the output from the previous decoder layer, and this XENC is basically the output of the encoder layer. So what it means is that the data is coming from the encoder in the form of keys and values. And guys, one more thing, see, here also we are using WQ, WK and WV. Guys, remember when we studied encoder at that time also, while calculating, while working on a self attention task, we used WK, WQ and WV, right? And in decoder, the decoder masked self attention task, which I've shown you a few minutes back only, over there also we used WQ, WK and WV. And in cross attention also we are using WQ, WK and WV. Now what are these? So these are separate weight matrices, they are not related to each other, these are learned separately. Okay, so what this concept conceptually means, what is happening over here? So it simply means that coder is asking question using queries, and encoder is providing information using keys and values. So decoder is basically asking, given what I have generated so far, which part of the input sentence should I focus on now? And for this task, attention need to be calculated. And for attention computation, we will use the same formula. And now you know this formula, so I'm not going to explain it again. So after that, you will get the output of shape t into 512. And guys, as I've told you, we have 8 heads running parallelly. So the output of each head will be this. And after concatenation, we will get this. And why we are getting this? Because we have 8 heads and the output of each head is 8 into 64. If you'll multiply 8 into 64, you will get 512. So after concatenation, we have one output matrix of size t into 512. And then we use linear projection, and what this weight matrix is, how we got this size, all this part I have explained in the previous video. You can get it from there, you can understand from there. And after that, final cross attention output will be this. Guys, see, the output shape is same, t into 512 tokens, number of tokens into 512. And why we are having the same shape? Because I've told you that we are performing add and normalization layer after each sublayer of the decoder. So for that, so after this multi-head cross attention, we have add and normalization layer. Okay, let me show you the architecture once again. See, now after this layer, the output shape is t into 512, and the input to this is of this shape. So we can perform element wise addition on it, and then we can perform normalization on it. After that, we have feed forward network. And guys, this feed forward network is entirely the same as we discussed in encoder, so we are not discussing it. And after this feed forward network, you will perform add and normalization layer, then that will go to the linear layer. Then we have a softmax layer. Softmax layer will provide the probability values for the entire vocabulary, and from that vocabulary, the token which have the highest probability will become the next token, and then that token will become the input again over here. And the shape of the input matrix will change depending upon the number of tokens. Remember, when we have 2 tokens as input, at that time the shape is this. And let's say if you have 76 numbers over here, then over here your matrix shape will be 76 into 5 and 2. So guys, this is what a decoder is, and I hope this video is helpful. And guys, if you like my content, please like, share and subscribe my channel. Thank you for watching.